Hello guys, I'm here to explain the research paper which we have implemented, StegoGAN. It's basically uh, the remaining papers which were done up to now. They are generating images from the same domain. Like generating images. If you check here, there is horse image. In previous GANs, like in previous papers and all, they generate new horse with the same domain of images and horses. Here we are trying to generate images with two domains, and though there are previous work generating the new image from the two domains which are called non-bijective image translation. Here you can see in zebra image you can see there is an elephant. When you when you're when you're generating it generating a new image, the elephant characteristics also comes there. We are trying to omit that. That's where a novel approach comes StegoGAN, leveraging steganography for non-bijective image-to-image translation. Now, I am going to explain you the architecture. Yeah, here comes the architecture. This is the training architecture methodology they used. The main methodology they used was to hide the unmatchable things and give the new one. Like here uh, here they will hide that elephant part and generates the new image from the horse and the zebra. That's what the thing they are trying to do. Now the, now I am going to explain the process what they did. First, this encoder. Here in this encoder, they use ResNet style of encoding, like uh, translating an image into a text format or any other format. So from that from that it from the two domains, in our case we developed a, they developed based on three domains. One is plain LN that is nothing but generating an maps image using the aerial image, using the aerial satellite image. They trained using both aerial and the maps image, and then liver data set and one another. We took the plain LN part and we tried to implement it. Here comes the approach. In this encoder, we use ResNet style of encoding, so we get the textual format of the image. Here comes the main part, the mask predictor. Using from the domain B, it predicts the mask which are matchable and which are unmatchable. And this unmatchable thing, this matchable things goes to decoder, and this decoder gives the clean output that means from aerial image to maps image, that is A to B. Now here comes the steganography concept. In this steganography concept, we are hiding the unmatchable things. We are not deleting it. So here comes that we can also extract A again. This is how we try to hide. We will hide the unmatchable things, and then we get the stego output. That means mixing unmatchable things and matchable things. Next, we use patch GAN. That means we will try to we use discriminator that analyzes the a single part of image. Like if you give three as a patch, it will analyze for every three into three image. It separates and analyze the all patches. That's what the discriminator does to like discriminator to classify that real or fake the generated images. Next, this goes to reverse generator, and then it will generate an image with the both unmatchable and matchable things. Then we can get the then we can get then we can get that again that may input image which we given here, and we can get easily now here. That's what the thing they did, and we implemented it. And here comes the architecture where the application flows goes. We'll give the input as aerial domain, and it goes to encoder. This encoder changes to using external generator, changes to textual format. This mask predictor, uh, it's trained from because we trained our ML model there. Here, like deep learning model there. This ML model predicts the which comes under matchable things, and which comes under unmatchable things. These matchable things directly goes to decoder and gives that output of the map. And then next, while generating the input image, we'll combine the both matchable and unmatchable, and then gives to decoder. Then we can get the image output. Here, we'll go with the we'll go the we'll go with the sample execution. Here we'll give in aerial image as an input. Yeah, this is the input image we given. It's a college image, VAT college image, and then here you can see that it returns only the maps thing, like only roads. It gives only the roads thing, like it deletes the all the trees, buildings, and all. It hides that using mask, and then while again it can regenerate the input image again from the B. Here comes it. If you see, there was no mismatches between the input and B2A. This was the thing they did, and there is a slight brightness issue. That's it. Other than that, it's really it's looking like very likely. So that's what the thing they did, and then we trained it up to 323 epochs. This was the last. This was the last results we got. This is the FID, which you got is 58.5. It is it is very better. It is that means the image quality is very better. And then KAD, it approx 0.02. That means after conversion it comes under 2.0. That means it's really like very good image. And then the RMSE we got was 10 10 loss. In the paper they got up to 18 to 20. Since we fine tuned it more, and then we used high resolution. We changed it to 512 into 512. We got the high quality images, and the accuracy was also very good. They got like 64 and 74, and we got 79 and 84. And you can see these are our results, and we'll show their results, how what they got here. RMSE they got was 822, and the accuracy is 60. Accuracy for sigma square is sigma 2 is 66, and for sigma 2 74.8, and FID got 58.4, and KID is 2.4, and we got the KID as 2. And you might get like you might get a doubt that they got 58.4 and we got 58.5, but the accuracy changes. This FID is subjective to the library we are using, and the plus two or minus two, it varies from libraries to libraries. So we will not see that much. And then these are our key findings at last. Uh, the future, we want to include another approach, like here you can see the mask predictor generate masks from only from the domain B. We are trying to get the context from the both the domains, and generate mask accordingly. So we can also preserve the tiny details. But for that we need extra dataset, which is worst case images and all. We need that. So since we fine tuned it from this, the So though the image looks similar, but through this we can also preserve the tiny details if we want to. If in this domain, in this maps domain, we may not require, but in other domains it will be useful